What is going on, everybody, and welcome to part 6 of the Deep Learning with PyTorch tutorials. In the last video, we talked about the basics of convolutional neural networks, as well as building our data set and actually kind of pre-processing the data set to get it ready to be passed through a neural network in PyTorch. In this tutorial, what we're going to do is actually build that model and do at least some training of that model. This one's going to be a little slower just on the CPU, so we're just going to do a little bit of training, and then in the next video we'll have to talk about how do we speed that up on the GPU. So with that, let's get into it. So this was the code from before. I just kind of condensed it all into one cell. Just builds the data, and we've got training data accessible, so I just run that real quick, make sure. Yep. Okay. So now let's actually build the model itself. So we're going to import torch. We're going to import torch.nn as nn, and then import torch.nn.functional as big F. Now what we're going to do is class net, and again it inherits from nn.module. And just like before, we have to define an init method and immediately call super module. So, super init ionit. Okay, cool. Runs that. Now we're ready to actually start making our layers. So to make our layers, we're just going to do basically the same thing we did before. So we're going to say self.conv this time. We'll say 1 equals nn.conv2d, and don't forget to capitalize the C in conv. And again, just like before, you've got inputs and outputs, and then one more thing. So the input is 1, it outputs 32 convolutional features, and then we have a kernel size. So this is a 5. So this is going to make a 5 by 5 kernel or window as it rolls over our data to find features. So, okay. So that's our first layer, and then what we're going to do is we're going to make 3 convolutional layers. So I'm going to take this, copy, paste. We're going to say 2 and 3. And just to note, these are convolutional, 2-dimensional convolutional layers. Torch, I'm assuming, has 1D and at least 3D, but you can use as many dimensions in your convolutional layers as you want. If it doesn't exist in Torch, you could code it in Torch. But interestingly enough, convolutional layers like 1-dimensional convolutional layers, so 2-dimensional convolutional layers, this would be used on images, right? Images are 2-dimensional. 3-dimensional is used on like scans or models, stuff like that. And then 1-dimensional data can actually is at least recently being used on even like sequential or temporal type data sets with a thing called attention. And basically, it seems to be outperforming recurrent neural networks, which were kind of the industry standard for doing any sort of sequential type of data. So anyways, just know there are other types of convolutional layers. It's not all for imagery, but imagery does seem to be the main forte of convolutional layers, as well as just neural networks in general. I mean, it seems like most people are using convolutional layers nowadays. So, anyway, so we've got our 3 layers. Let's make it a little more interesting. First of all, this one takes in 32. We're going to say it outputs 64. That means it takes in 64. And we're going to say it outputs 128. Now, at some point, this neural network needs to have linear layers, right? It has to eventually at least output to one linear layer that would be the distribution of predictions, right? So at least one 2-node linear layer we have to get to. But getting to that is actually kind of difficult, and if you just follow the tutorials on like PyTorch, I just don't think they tell you. It's this gaping hole. And it was also a gaping hole in TensorFlow. I haven't gone through TensorFlow's basic documentation in a while, but also, since TensorFlow has adopted Keras, Keras has literally a flatten function or method. I can't remember which one it is, but it has a thing called flatten, and it's super simple. In PyTorch, this doesn't exist, and as far as I could find researching this, there is no good way to flatten the information. So the only way I know to do this and it appeared to be this is the only suggested way as well, is to actually pass data through, just fake data, right? And figure out what's the shape. So that's what we're going to do. But if you look, for example, at this is an official PyTorch example for MNIST creating a convolutional neural network. The main issue is anytime you go from convolutional layers to fully connected or linear layers or dense layers, you'll see them called all kinds of things. How do you get the input number? Because the input number isn't 50. And then you see like it's 4 times 4 times 50. Where's the 4 coming from? We don't know. Where's the 50? Is it coming from up here? Is it referencing that 50? What is that referencing? We don't know. We have no idea. So anyway, or is it maybe this 5 minus this 1? So 4 times 4, and then like you legitimately don't know. But then also these aren't actually the outputs. The outputs come after you apply a max pooling to the convolutional layer. So is it 2 by 2? So is it because these are 2 by 2s? They're size 4 times 4? I don't know. We have no idea. We just have no idea. So that kind of sucks. I wish they would explain it better, but I feel like they just gloss over it. So how do we get there? So the way that we're going to get there is we're just going to start off by defining some, because basically what we want to do is we want to say self dot, and then we'll say fc1, and then that is going to be equal to nn dot a linear layer. But the question is, what the heck is the input? And then the output, let's do 512. So it'll just be a 512 dense layer. And then we'll say self.fc2 equals nn.linear. This one would take in 512. And let's say it returns 2 because we have 2 classes. So in theory, this is our target for the entire data. What would be really cool is if we could just say -1 right there. Like, take anything, please. But we can't. So, at least not to my knowledge. That would be really cool if we could. So, how do we get that number? So, the first thing that I'm going to do is I'm just going to specify x equals torch.randn, and we're going to do a, we're going to do a 50 by 50, and then we have to reshape or view it as a -1 by 1 by 50 by 50. So again, so this is where these are the ones that relate to each other. So however many images we have, these are all going to be in their tensor form 1 by 50 by 50. So the actual tensor that we pass through the neural network will have this exact shape. So however many feature sets we have times 1, 50, 50, that'll be the input image. So, okay. Okay, cool. So we're going to say self dot, and then we'll just say 2 linear equals none. And then what we want to do to get this, to figure out what the number needs to be to this layer, we have to, I'm just going to comment these out so I can actually run this first. We have to know like what to pass through here. So we need to run some data through these 3 layers. And then once we get the output, we can just check the shape and then multiply the dimensions. So if the dimensions were 5 by 5 by 3, it would be 5 by 5, 25 times 3, 75. That would be our flattened shape, 75. So what we need to do is pass some data. The way that we're going to do that is just by creating some random data. And then we're going to pass that through self.convx. Now we're calling convs. This is going to serve as part of our forward method, but not the whole forward method. So we're going to say define convs self. It also gets x passed. And what we're going to say here is basically this is just like the forward method. It's just we're only going to run forward these 3 layers. Okay. So, so what we're going to say is x equals f.max underscore pool 2d. Then we're going to apply max pool 2d to the layers. So they're doing it a little different here, just for the record. So basically they're saying, okay, f.relu, that's exactly what we used. It's the same kind of thing. We just did a rectified linear on the output neurons, basically. And then here, they're just running max pooling over that output, and then they're just kind of cycling. But I think to me, I think it makes more sense to put it all on one line, but just know there's many ways that you could do this. We're just applying this function to the data. So max pool 2D, and then we're going to do f.relu over self.conv1, whatever x is, and then the shape of the pooling, we're going to go with 2 by 2. So then we're going to do that for those 3 convolutional layers, paste, paste. And then we're going to do a quick check. So if self.toLinear is none, I almost did double equals none. Nice. Self.toLinear equals, and then we're going to say x 0th dot shape. So x 0th dot shape 0th. I want to make sure I get this right. And then time, so basically it's going to be, yeah. So it will be the 0th shape 0 times the shape, the 1st shape times, whoops, time, bro. times that second value, because it's going to come in with these 3 values. So, so for example, because x, just keep in mind, x is coming in as like a batch of data. So we're going to say that 0th element. So again, this -1 denotes, hey, it could be any size of data. So that's why we're saying 0th. So we're just saying the first one. In this case, we're literally only passing really, truly 1 element, but it is a batch of just happens to be 1 element. So we pass that through, and then we're just grabbing the shape of that data. So, so that sets that value, and that just sets it globally to this object because it's just self.toLinear. So then all we're doing now is return x. This way, and I'm not leaving this behind yet. We're going to do some printing, but this way we return x, and then we can go and actually create our forward function, or our forward method, rather, forward self x. And now what is going to happen? Well, immediately we're going to say x equals self.convs x, because why would we, like, we would just copy and paste this code, or we could just call convs, right? Well, no reason to copy it. And this won't run anymore because we set it so one time and we're done. Although this calculation wouldn't wouldn't be a big deal. It really wouldn't. Okay. So we run the convs, and then we'll just finish this, I suppose. X equals x.view, and then we'll say -1 self.toLinear. So we reshape that to that to be flattened, because after it comes out of those convs, it's not flat yet. So not only do we need to know the number before we call it here in the initialization, which let's go ahead and do that before I forget. So it's not -1 anymore. It becomes whatever the value of self.toLinear happens to be. So as you can see, right in the initialization of calling these layers, we actually have to do a quick forward pass to see what's that number, which again is just kind of lame. And I'm sure, like, I'm trying to decide, like, I don't know what TensorFlow does when you call flatten, but it would just be nice if we could just do that. But anyway, okay. So we need to run that forward pass to determine the number for here, and then again to determine it here. So both there, both in the initialization and in the real forward pass, we also need to know this number. So then self.toLinear, actually self.toLinear, and then what we're going to say is x equals f.rectifiedLinear over self.fully connected 1 x. So here we pass through all the convolutional layers, we flatten it, we pass it through that first convolutional, or first fully connected layer, pass that through here, and then we still need to pass it through this final, the final one. So all we're going to say here is self.fc2. So x equals self.fc2 x, and then we'll return x. Woo! Okay, so now that we've done that, we are ready to, I think, well, let's print out a couple of things. So let's print out up here. pool. Let me print. I'm trying to decide what I want to do for that. I guess here, let's just print x0. So print x0 dot shape. Cool. So we'll go ahead and print that, and we'll actually see the output. So what we'll say is net equals net. Oops. What do we got? We got 32 channels expected. 32 to 32, okay. I'm actually not positive on this one. Let me make sure that ran, but I'm pretty sure it did, yeah. Okay, 3155, that's our conv. So the input, we got 32 channels. 1 to 2. Oh, I bet I know what I did. We copy and pasted here. Yep. I was like, yeah. Okay, so we copy and pasted up here, and we forgot to modify the values there. That was stupid. Okay, rerunning that. Cool. So we have, so we can see the shape is a 128, 2, and 2. Okay, so we can see, okay, max pooling was a 2, 2, and then it output 128. But then, you know, we come over here, and here, yeah, the output is a 50, so it could almost make sense. But then we look at their max pooling, and it's a 2 by 2. So, anyway, so as far as I know, there's no really great, just like quick and dirty calculation that we could make to determine that flatten. The best thing that we can do is actually just pass the data, and we only need to do it once. So at least it's not the most beautiful code. Someone coming from, the main issue is someone coming from a different library or something looks at this and is like, wait, you know, why are they running this? You know, it doesn't really make much sense. So anyway, it just makes for ugly code. So I really wish PyTorch make a flatten. Everyone knows what that means, so just do it, please. So anyway, and they might even have a flatten, but I don't think it would apply yet to just like a layer, like in abstract. And maybe that's the problem. Like maybe that's why it works on TensorFlow, because you define your graph first, then you pass data. So because the graph is defined, it's there. It can be queried. You know, so I don't know. Maybe it's not possible, but I feel like at least it would be nice if they would help us to make this code better looking, I guess. Okay, that's enough. So, one thing I almost forgot is the activation here. So, I think I actually made this mistake in the first machine learning or first deep learning tutorial. So I think it's kind of just a tradition for me to forget this, but in theory, you probably need some sort of activation layer here. Like I said before, though, activation layers aren't really required. You don't have to have them. I wasn't really certain, like surely you could just run these layers, because again, it's just a bunch of these vectors getting multiplied against each other. so you can do whatever the heck you want. So you actually don't need an activation layer here, but you probably should have one. So rather than just returning x, return like, I don't know, f.softmax. We'll go with that. And then again, dim 1 because of the batches. So someone asked before to please re-explain dimensions. I really don't think I can explain it any better than I explained it before, but basically the x coming through here, so x here, the x is a batch of x's. So how would you reference the batches, like the batches, right? would they be, so the 0th dimension would be all of the batches. We don't want a softmax. We don't want this distribution across the batches. We want the distribution, and by distribution, I mean from 0 to 1, or really it's more of like a percentage, right? We want it to be distributed across cat and dog, these two things. So the 0th dimension would be all of the batches. The 1st dimension would be, okay, between cat and dog classifications, let's get an actual distribution of, you know, prediction percentage confidence or something like that. Anyway, cool. So yeah, one thing, I'm probably going to forget to do it, but try, after we do the GPU thing, I really don't feel like testing and showing you things while we're on the CPU, because it's just kind of slow. But later, if I forget, return X and fit and train. I can almost guarantee that is going to work just fine on this problem, but on much more complicated problems, it can help to have activation functions, but especially on the last to output, it probably doesn't actually matter. But yeah, okay. So later, if I remember to, we can remove that and just kind of have fun, because neural networks really are just a bunch of trial and error. Like, everybody kind of does a lot of the same stuff as everyone else, but just understand that nobody knows what they're doing. Like, truly, nobody knows, because nobody understands how neural networks work. So anybody who claims to be like this, you know, expert at neural networks is a dirty liar. So anyway, cool. So that's everything we need. So we actually could start passing data through. And at least to start, I think we could do some of this. My plan was to kind of pass information through and iterate over our data. I'm not really sure I want to stuff that into this tutorial, though, because it's going to be slow. But in the next tutorial, I really want to talk about GPUs. So let's go ahead and throw it in. Bonus time. Import torch.optim as optim. And really, we've talked about a lot of this stuff already anyways. So optimizer equals optim, and we'll go with the atom optimizer again. And then again, it's net.parameters. And then we'll go with the learning rate of 0.001. Don't have to explain that. Already did it. Loss function equals MSE loss. Yay, mean squared error, finally. So now, what we're going to do, the first thing we need to do is we have all of our training data here in this training data parameter. So what we want to do here is we want to separate out the x's and the y's. So we're going to say x equals torch dot tensor, because we want to make it a tensor. And then what we want to do is reshape all this. So we're going to say I0, because it's the, we're trying to get just the x's here. So I0 for I in training underscore data. And then we're going to dot view as a -1 by 50 by 50. Beautiful. Then what we'll do is x equals x divided by 255. Again, in this task, we could probably get away by not doing that, but all we're doing here is scaling the imagery. So the idea is right now the pixel values are between 0 and 255. And what we really want them to be is between 0 and 1. So that's how we're doing it. So cool. Then we're going to do our y. So again, it'll be just torch.tensor. And then in this time, it's going to be I1 for I in training data. Okay, so once we've done that, the next thing that we want to do is separate out some training and then validation or testing data. So the way that we're going to do that is first we're going to grab a val percent, let's just say 0.1. So our target will be, hey, let's test against 10% of our data set. So val size will be equal to the integer of the len of x, so however much x we have, times that val percent. So let's go ahead and print val size. This might take a second because we got to, this operation probably is what's taking the longest, is just converting this information, but cool. So about almost 2,500 will be our validation test size. This should all make total sense. We're converting it to an int here because we're going to use this as a number to slice with. So it needs to be a valid index. It couldn't be a decimal. So then we're going to have train underscore, and we'll say capital X here, equals x. And we're going to say up to the negative val size. So this is just basic Python slicing here. So train X, train Y, and then this will be test X, test X. This will be test Y, and this will be train Y, and so it'll be Y up to the negative val size, and then here it will be negative val size onward. Negative val size onward. And again, just to make sure, print len train X, and then we'll say print len test X. Okay, and those numbers line up, so, you know, just in case we did a slice wrong or something like that, it's probably a good idea just to check it one more time. So then we're going to actually train, so we need to determine whatever batch size we want to use. I'm going to say 100. If you're getting a memory error, lower the batch size. That goes for really any task at all, like if you download some code off the internet. The quickest and easiest thing for you to change if you're hitting memory errors is the batch size. Now, obviously, you don't want to go down to 1. Generally, if I can't run more than like 8 in a batch, then I'm going to start tweaking and decreasing the size of the model itself, like the layers, how many nodes per layer, that sort of thing. But the very first thing that you should try to modify is batch size. And then we're going to be running on the CPU. So for epochs, I'm just going to say 1, but later we'll do many more. But then what we're going to say is for epoch in epochs, what do we want to, or actually, range epochs. What do we want to do? Well, we're going to say for I in TQDM, and we're going to say range of 0. So we want to start at 0. We want to go for the len of train X, so however much training we have, and then we want to take steps that are the size of our batch size. So I think probably the best thing is to just print I, and then I plus batch size. Let me just run that real quick. What the heck? For I. What did I do wrong? Oh. Okay. Range. TQDM range 0. I just screwed up my parentheses here. This should be the range function. Run that again. Yes. Okay. So what are we looking at here? So these are going to be our slices through the actual training data. So it'll be, so the first batch will be the 0th to the 100th index. And then the next batch will be the 100th to the 200th, and so on, all the way through our entire training data set. So that's what's going on there. So yeah, hopefully that wasn't too confusing when my parentheses were off. But yeah, so TQDM is just so we can have a nice progress bar, which would be much nicer if we're not printing things, but I wanted to print just to show you guys what's happening. And basically, yeah, we start at 0, we go to the length, and we take steps the size of the batch size. So then, well, all we have to do is say batch underscore X is equal to train X, and then yeah, it'll be I colon I plus batch size. And then again, we want to reshape, so we're going to say view -1, 150 by 50, and then batch Y will be equal to train Y, and then same thing as before, I plus batch size. Cool. So now what we want to do is we're actually going to do the fitment. So every time you're planning to do fitment optimization and all that, you need to zero the gradients. Now there's two ways you'll see people zero gradients. So you're going to have net.zeroGradient, or like whatever you've called. Like in our case, net is corresponding to our model. So you might also see people use like model.zeroGrad. But then there's also optimizer.zeroGrad. So what's the difference? Well, as long as here, so when we ran optim atom, and then net parameters. So all of the parameters are being controlled by this optimizer. If that's the case, then there's really no difference between net.ZeroGrad and optimizer.ZeroGrad. You could use either one interchangeably. That said, sometimes you're going to have a model that actually has two different, like it's a model that's built with two different neural networks that might have different optimizers on each side or something like that. Or, you know, there's going to be times, at least it's possible to have multiple optimizers because you have two different neural networks that come together to build one large model. If that's the case, then you want to use the specific network in question. So you've got one, and because you could also have an optimizer, but in two different scenarios. So it could be the same atom optimizer, but you've got two. You got optimizer 1 and optimizer 2, or something like that. So just think about your problem and decide which way do you need to be explicit. Are you trying to say, hey, for the entire network, zero the gradient, or are you saying for just this optimizer, or are you saying, you know, so you just need to know which is which. Okay, so probably for most people, it's always going to be just optimizer.ZeroGrad. But if you want to be really specific, especially if in your forward method or in your loop, your training loop, you're training the whole model together, but maybe you're calling different spots separately or something like that. Probably the safest thing to do is to do a net.ZeroGrad, but it really is going to depend. As long as you only have one network and one optimizer for that entire network, you don't really need to think about it beyond that. But just wanted to bring that up because you're going to see people doing different things. Sometimes they'll use their model name, or sometimes they'll use the optimizer name, and you're like, whoa, wait, when should I do what? So anyway, net.ZeroGrad, either one you want. Then what we're going to say is outputs equals, and it's going to be net batch x. So this gives us our outputs. Now we can calculate loss based on what are the outputs and what were the desired outputs. So we use the loss function we've defined up here. So we can say loss equals loss function, and then it's outputs, and then batch underscore y. Then we're going to loss.backwards. So we're going to apply that and backward. And finally, optimizer.step. And once we've done that, we can actually go and train this model. So what I'm going to do is we're not going to print anything out. And then maybe at the very end, we could print loss. Print loss. But this is going to take a really long time, most likely. We can print loss, and then maybe while that's going, yeah. So while that's going, we could talk about like how we could actually, we could predict on the model. So, so what we're going to do is we're going to say correct equals 0, total equals 0. And then with torch.noGrad, also someone brought up before, there is still model.train, or so net.train, net.eval, and at least in our case, it doesn't really matter because we don't like have dropout, but if you did, you'd want to have everything activated for when you're actually evaluating your model. We'll possibly talk more on that later. I didn't even think about that. That was really dumb. But of course, that makes total sense. That the same principle applies in like TensorFlow and stuff like that. So anyway, there is still a valid use of .eval and .train, and you'd want to remember to switch those on and off if you went back and forth. So now, let's just quickly test. We'll do this super inefficiently, but that's okay. For I in TQ DM, range of the len of test x. For that, what do we want to do? Well, we're going to say real class equals torch.arg max test yi. And then we're going to say the net out is equal to net test x I dot view as a -1, 1, 50, 50, And then we want the 0th element. That would be the net out. Now, predicted class would be equal to torch.argmax of net out. If predicted underscore class is equal to the real class, correct plus equals 1. I really wanted to beat this, but I didn't. Dang it. Otherwise, either way, we're going to do total plus equals 1, and then we can print accuracy round. I see the error there, but we'll get there in a second. Correct divided by total to 3, and then replace this with a comma. Whew. Okay, let's see what our accuracy is now. It's probably nothing good, but we'll see. Zero. How could that be the case? We should have at least gotten a 50%. Let me think about this. What did we do wrong? For I in TQDM, test X. I'm trying to decide. I really can't. I'm not running everything again. Test X. Let's just make sure. Yes, there is something there. Definitely there was something there. Real class. Test YI. For I. Test XI. Output. Let's do print real class. And let's print net out. What? So test Y we must have typoed. Yeah. Oh dear. Can I get away with this, I wonder? Test Y. Train Y was correct. We would have hit an error anyway. Test Y. I think we should be able to get away with just redefine that, come down. What is this? Disgusting. What am I looking at there? Oh, because of this. Okay, well, we still got to kind of do that. 0. Okay, so now, where's my TQDM? How come I don't get my progress bar? It's kind of weird. Where is my progress bar? Oh dear. Right as I redid it, apparently it popped up. Why would the progress bar take so long to pop up, I wonder? I don't actually know. Anybody has any idea why that would take so long? I don't know. Okay, now we have an accuracy. This video has been way longer than I intended, but there's just so much information I have to cover, plus I hit a couple of errors, but I really sometimes, actually, no one really complains about the errors anymore, but just in case you're feeling it inside and you just didn't want to say anything, I do like to leave them because these are errors. Like if I hit an error that like I'm like, oh, that's just me, no one else is possibly going to hit that, then fine. But these are all things that you're going to have because you're going to copy and paste this stuff. You're going to forget that stuff. You're just going to keep making lots of errors. Trust me. So hopefully you don't mind that I leave them in there. I think they're pretty useful to leave in. Okay, so now what? Well, first of all this stuff is going by really, really slow. The slowest thing is actually, training this model. It's very, very slow. Now, if all you have available to you is a low-end CPU or whatever, or even a high-end CPU, but if all you have available to you is a CPU, that's okay. You can still follow along. You can at least train stuff so things start taking steps at the very least. But moving forward from here, I am going to assume, or I'm going to use a GPU. You can use whatever you want. But in the next video, I'm going to show how we can convert this code to be PyTorch on the GPU code, and hopefully, at least if you don't have access to a GPU, honestly, lots of cloud GPUs are pretty cheap. There's also Google Colab. There's like Azure has, I guess, credits. I think if you have an edu address. I haven't confirmed this, but apparently you can get like $200 in credit if you have a GPU or a GPU address, an edu address. But most places that will give you credits won't allow you to access the GPUs. So I could be mistaken there, because obviously people are going to like mine crypto and stuff. So jerks, ruin it for everybody. But anyway, so there is stuff like that. Otherwise, you can rent GPUs in the cloud for pretty cheap. You don't need them for very long. So you rent them, you use whatever you need. You spend like usually like $1 or something like that, and then you're done. So anyway, that's what we're going to talk about in the next tutorial, is just the GPU version of PyTorch. And then we're going to get back to models, but the models and stuff that we're going to be doing is going to be kind of assuming you're running on a GPU. Because the next thing we want to do is like, okay, we got 64% accuracy. Now what? Well, we probably want to do more epochs of training. Like 64 is good. It's better than, random. Random would have been 50%. But, so do we want to train this for 3 more epochs? And after 3 epochs, if we did better, should we continue? Should we do 6,000? At what point do we stop training and all that? So we have to talk about how to actually read the statistics of our model, maybe visualize some things, how to actually figure out, should I keep training, should I not? And then maybe like if you want to change models, how do we compare models? Anyway, all that testing is what takes up the bulk of your time, and or at least takes up the bulk of your GPU time. So this is just time where you're sitting around doing nothing. So for that step, for that research step, it's just way better to have a GPU. So that's what we're going to talk about in the next tutorial. And then after that, we're going to talk about visualization and all that, and just analyzing your models. So even if you don't have a GPU or you don't have access to them, you can just watch the next one if you want. And then after that, you can still follow along. It's just things are going to take a lot longer to run for you than for us. So anyway, that's all for now. Shout out to recent channel members. They just brand new shiny channel members: Ralph Rodriguez, David Lavoie, AI Creations, and Anand. I'm going to just call you Anand, man. Loganathan. I'm sorry if I mispronounced that. Feel free to correct me below. Thank you guys very much for your support. It allows me to make extra long videos just like this one. Okay, I will see you guys in the next video.